Alright everybody, this video has sound, so hopefully everyone can hear my voice. We are in the Geometry Chapter 4 study guide, and this lesson is on section 4.3, so chapter 4, section 3. This one is on using side-side-side congruence. Now, in the last section, 4.2, we talked about how to prove that two triangles are congruent. And I said that if you have 3 pairs of matching sides and 3 pairs of matching angles, then if all 6 of those things are true, then you have 2 congruent triangles. Now, it turns out that you don't actually have to prove all 6 pairs of things, 3 angles and 3 side pairs, congruent. There are what I like to call shortcut theorems, okay? So you don't have to do all 6. So for example, this is our first shortcut theorem, side-side-side congruence. If you just throw out all the angles entirely and just show that there is 1, 2, 3 pairs of corresponding sides that are congruent, then you can go ahead and make a conclusion that those 2 triangles are congruent. So corner A corresponds to corner R, corner B corresponds to corner S, corner C corresponds to corner T. Remember that sometimes the triangles aren't lined up perfectly in the same orientation, meaning that they're looking at you in the same way, same direction. So you have to be a little bit careful. You can see that that's what happens here in this first triangle diagram. I've got 2 triangles. I've got triangle FGJ, which is over here on the left, and then I have triangle HGJ, which is over here on the right. They share a common side in the middle here, JG. And what I want to do is use the side-side-side congruence postulate to prove that these 2 triangles are indeed congruent. So the postulate would be the side-side-side congruence postulate. And so if I want to prove that all 3 sides are congruent, and I know that FJ and HJ are congruent, then I'll have to prove that FG is congruent to GH, and the third pair of sides is actually one and the same. JG is congruent to itself. Okay? So then I'd have 1, 2, 3 pairs of sides that are congruent. Once I have that, I would be able to state that these 2 triangles are congruent by side-side-side congruence. So creating a proof, we write our statements on the left, and our reasons for those statements on the right. And we begin with our given information. FJ is congruent to HJ, and G is the midpoint of FH. So how do I prove, these are the things I want to prove, how do I prove that JG is congruent to JG, that's this one? Well, according to the reflexive property, I can go ahead and make that statement right away. Any line segment would be congruent to itself. That's what the reflexive property says. But how do I prove that FG is congruent to GH? Well, according to the given information, G is the midpoint of FH, so this side of FH is exactly the same measure as this side, with G being exactly in the center. So, knowing that G is the midpoint, I can say that FG would have to be congruent to GH because of the definition of a midpoint, because G is the midpoint. So there you go. We had 1 pair of sides that are corresponding, stated congruent in the given. We had 2 more pairs that were corresponding, that we proved are congruent. So now we have 1, 2, 3 pairs of sides from one triangle to the other that we have proved is congruent. And according to the side-side-side congruence postulate, that's all we need. So I can now say that triangle FGJ is congruent to triangle HGJ by the side-side-side congruence postulate. Oops, not quite on the screen. There you go. Okay, are these two triangles congruent? Well, this side is congruent to itself. We've got these two sides that are congruent and these two sides that are congruent. So we do have all 3 pairs of sides that are congruent, as they are corresponding across from one triangle to the other. So I would say that according to the side-side-side congruence postulate, I could definitely make these two triangles congruent. Well, on this one, is RST congruent to TVW? Well, RS would have to be congruent to TV, and ST would have to be congruent to VW, which it is, and RT would have to be congruent with TW. Well, we've got 2 out of 3 sides here, and does that mean that the third side has to be the same length? Right? Would I know for sure that RS and TV would be the same? Well, we don't know that for sure. It looks like it's kind of the same, but if I have like 2 side lengths, let's say that this is the corner, this is one side, this is the other side. Would the distance from here to here have to always be the same as long as this length and this length remain the same? No. I could move my fingers closer together, make it shorter. I could move these 2 farther apart, make it longer. So these 2 sides didn't change length at all, but the distance between those 2, the third side, therefore, did. I can make it longer, I can make it shorter, and the first 2 sides are the same. So just because you have 2 pairs of sides that are the same on 2 different triangles doesn't mean the third side would have to be. So I would say that this is a pair of triangles that I could not prove. I'm going to say not necessarily congruent. Okay. Are these congruent or not? I would say this pair is congruent, and this pair is congruent, and this side matches with itself, so that's the third pair. So yes, by side-side-side congruence postulate, those 2 triangles are congruent, ABD and CDB. RST, and RQT, well, same thing. This is a pair, and then the overlapping side with itself would be the third pair. So yes, by side-side-side congruence, those 2 would be congruent triangles. And ABC and DEF, D is the corner you can't quite see under the fold here. So yeah, we have 1, 2, 3 pairs of corresponding sides. The way that they've written them in order matches. So this is also congruent by side-side-side congruence. Theorem. Okay, well, number 11. AC would correspond with DF. Yep, those 2 match. AB would correspond with DE. AB and DE, yep, those 2 match. So the question is, BC, this length, match up with EF, which is this length? Well, this section here is 2, and then this section down here is 2. So whatever this is, the distance from F to B, let's call it X, is E to F the same length as from B to C? I would say yes, because written as an algebraic expression, this would be the sum of the sections 2 plus X from E to F. And this would be the sum of the sections of X plus 2 from B to C. So is 2 plus X the same as X plus 2? Yeah. So it turns out that EF is indeed congruent to BC. Takes a little extra thought, but you should be able to come to that conclusion. So we do have 1, 2, 3 pairs of corresponding sides. So if we use the side-side-side congruence postulate, we can state that those two triangles are indeed congruent. Now this one fails in that regard because even though you have a pair of congruent 7 side lengths and a pair of congruent 5 side lengths, we can't use the same concept here because from F to E is 1 plus our unknown section, and from B to C is 2 plus our unknown section. So BC is not congruent to FE. So we would be able to say, well, it doesn't look like these two triangles are congruent. The proof has some given information, and it's also written on the diagram. AB is congruent to CD, BC is congruent to AD. Can I prove that triangle ABC is congruent to CDA? Well, yeah, I would want to use the side-side-side congruence postulate, and really all I would need to do is prove that side AC is congruent with itself. So this is very, very similar to a lot of the other theorems that we've done very recently. All you would do is you would start with your given information, the two pairs of sides that are already congruent, you'd want to establish the third pair of sides that are congruent. In this case, this side is congruent with itself. That's the reflexive property. And then once you had 1, 2, 3 pairs of sides that are all congruent, you could say that triangle ABC is indeed congruent to triangle CDA by the side-side-side congruence postulate. Alright, to complete the proof, we've got some given information we start with. Let's see, we say that triangle, or side AB is congruent to side CB, that's marked in the diagram. D is the midpoint from A to C. Okay, so we'll start with that. We can use the side-side-side congruence postulate if we can prove that AD, this length here, is congruent to DC, that length there, because those are corresponding sides on the two triangles, and that BD is congruent to itself. So I want to prove that AD is congruent to DC, and DB is congruent to itself. So again, this is very, very, very similar to one we just did on the other page and ones that we've done recently. A little bit repetition here with our examples, so we'll just keep doing them though. Alright. Okay, so I'm going to start with trying to establish that AD is congruent to DC. I know that that's true because D is the midpoint. So by the definition of a midpoint, I know that those two segments would have to match. This one matches that one in length. And then we just simply need to use the reflexive property to prove that side DB is congruent with itself. And then finally we'd be able to state that triangle ABD is congruent to triangle CBD by the side-side-side congruence postulate. Once we have 1, 2, 3 pairs of congruent sides, I'm going to say congruence, not congruent, then we can say that two triangles are congruent. Okay, well, I'm going to leave this question and then this activity for in-class work and stop there with section 4.3.